Good afternoon again. Here we're going to be looking at the link in between the work and the kinetic energy and the potential energy. A work appears because a force is applied when an object is in motion. For example, I'm pushing on this box, the box moves, that's it. During the displacement, if we look at before and in the middle of the displacement, for example, now and now, when I tried to snap my fingers, in one state the box was static, in the other state it was in motion. That is because there were some forces that caused the displacement. When we go at it, when we say that a force is a transfer of energy, one of the easiest thing is to think about it this way. A force acts on an object, it causes an acceleration by Newton's second law. If it causes an acceleration, that means it changes the velocity of the object. In this case, I went with a linear force. It just changes the speed, the magnitude of the velocity. So if we have a force that changes the velocity, that means that over some displacement, it does a work. But if the force changes the speed, that means that the kinetic energy also changes. I can't recall the exact derivation. I don't believe I've ever done it either. But the end result is that the work done by a force will be equal to the change in kinetic energy of that object. You have a change in kinetic energy, there was some force that did a work, and the two are equal this way. For this, we really only look at the final state and the initial state of the situation, or where we're interested. This initial and final state don't have to be the very beginning and the very end of the situation. They just have to be two different moments of the situation. In between, there will have been a work done by this amount. The link with potential energy is very, very similar. If you look at this marker that I will throw in the air, if we look just at the upward motion of this marker, it starts with, just as it leaves my hand, some initial speed that we don't know, but we know it's going up. And it ends its motion here with some final speed of 0. It started here at a height of 0, and it ended here at some unknown height that is greater. We see that there's a change in kinetic energy by the fact that we don't have the same velocity. Where did that energy go? Well, it went into the gravitational potential energy. Remember, if I start here, the marker wants to go down and not be caught by my hand. It wants to minimize its potential energy. As it goes up, its potential energy increases till it reaches a maximum. So there also was a change in gravitational potential energy. And that change, all of the kinetic energy that was present right after the marker left my hand, is now in potential energy at the very top. So these two things in magnitude are equal. In signs, they're going to be different. There's a work done by the gravitational force, in this case, that points against the displacement. Here, this big green arrow is the displacement. At every point, we have the gravitational force. Since the angle is 180 degrees, Fd times minus 1, F times d times minus 1 because of the opposite directions of the vectors, that's our work. But we know the work is the difference in the kinetic energies. So really what we can write is that the work is the change, negative the change in gravitational potential energy. This, however, is just the work done by the gravitational force, by no other force whatsoever. A similar analysis to what we did to link the work in the gravitational potential energy can be done to link the work in the spring potential energy, and it yields the same result. When we observe the change in spring potential energy, and then we try and find the work related to that with the spring force and the definition of the spring force that we don't have here, we find that the work done by the spring force is equal to negative the change in spring potential energy. If we wanted to do the analysis or a similar analysis for another work with another what's called conservative force, we would get the same result, a negative times the change in potential energy of that force. That would go for the electric force, for example, in the electric potential energy. If memory serves, it's always the case. There might be exceptions that I forget because there's often exceptions to any rules that we throw at you. But if memory serves, only conservative forces have potential energies. And to find if a force is conservative or not, we need to determine if the work done by that force depends on the actual path taken or not. For example, the work done by the gravitational force doesn't depend on the path taken. If we take this marker here and we let it go, and it goes down and I catch it, the change in potential energy only depends in between the initial and final state. The work done by the gravitational force also only depends in between, or turns out is the same value. If we were to do this, the work done by the gravitational force would be exactly the same. And this as well. For something like friction, or an external force, or you for that matter, when we act on stuff, the work we do depends on the displacement that we cause the object to have, over which friction acts. And so those two things are the only what's called non-conservative forces that we'll worry about. For our purposes in mechanics, there are two conservative forces. And those are the spring force and the gravitational force. With the same token, there are two non-conservative forces we'll need to worry about.